And our speaker, Professor Jazar, he got his bachelor from Tehran Polytechnic and his PhD from Sharif University. I mean, the two highest ranked educational and university in Iran, and they really take only the cream of the university students. And Professor Jazar has also worked for many years in other universities in US and also in Canada. He's an expert in linear and non-linear dynamics. Actually, my knowledge in linear dynamics, I love the mechanics of points. But when it gets to rigid body, I become lost. So that's something I think where Reza starts, just looking at vehicle dynamics. And Reza has published very many papers. He's really he has got lots of innovations or theorems, related theorems in this area, and the result of his work has been communicated to the scientific societies through 200 papers, 10 books. Actually, one of his books has been adopted by 50 universities in relation to vehicle dynamics, and this is remarkable. And so, yes, it's a really great pleasure for us to having Reza here as a member of staff in our department and also the leader of our mechanical and automotive engineering discipline. And please join me in welcoming Reza. And, I wanted to say that Reza is also a true gentleman and a true scholar.
So thank you very much. That was fantastic introduction. Thank you everybody for coming here. And usually I'm a shy person and I can't speak in front of my boss who is here. I appreciate his presence. This seminar, weekly seminar, is a little bit different than normal seminar that we give in conferences, mainly because we know each other, we live together, we work together, and we know our past, present, future, our goal, and so on. So this type of presentation here is a little bit more friendly than normal presentations, as I said. So I want to share with you something that is my interest. Since I was a kid, I was collecting jokes. I love jokes, especially the intelligence behind jokes. What is the point that makes the joke funny? But because of my job here, I can't be that much funny. If you are funny, people don't take you serious. I know that, so I'm watching myself. But it's my interest. I collect them, and I love them when I read them. What is behind that? What is the actual point that makes this wording funny? This is the introduction here. I love it. It's fantastic. Let me give you another example. What is behind that makes it funny? It's very good. So I'm going to give you this coming soon. Next year, I'm going to give you a presentation about joke structure from engineer viewpoint. Why? Because when I collected them, there are probably 10,000 right now. I classified them, categorized them, and find out that there are some streams that you can make jokes in that streams, and all of them are the same. Don't take me wrong, it's not kids joke, adult joke, polite. This is not classification. Classification is different. I invite you to that presentation next year, then you're going to enjoy that. Basically, you learn how to make jokes. If you want, I can make one joke right now. But anyway, if I had time, I can make that joke at the end of my presentation. So let's get serious. Some people are here to see what is the new book from Reza. This is new book from Reza. Appeared January this year. 3 more books in the oven. By the end of this year, it's coming. So we go, and this is my talk. Now everything is serious. A few years ago, in 2010, 9-10, I introduced a new algorithm called, I named that auto driver algorithm for autonomous vehicles, especially for vehicles on the road. When you are on a road, you are following a line, so one-dimensional motion. When you are on a field, two-dimensional, more freedom. So the categories are different. And then I work on that, and I'm going to develop something because of difficulty to solve differential equations online fast enough. In this today, I'm going to show you or investigate how close are response of vehicle according to steady state equation to the transient equation. And if it is close enough, in the future we are going to use them, and I'm going to talk about that. For those people who are not in this area, I give you some introduction to get to the point, what is the vehicle dynamics and what is the category of the equations that you are solving. No matter what is your car, Audi or I don't know, my car, Chevy Malibu, $15 car, the only reason that you can maneuver, you can move, are those 4 points that we generate forces. It doesn't matter what is the CD player of your car. You have to generate forces under the tire to be able to move your car. We move all forces to the mass center of the car, okay? And then car is a rigid body, and those equations makes the equations of motion. We make another assumption and assume that the car is planar. Planar means no bounce, no Z movement, no rotation about X, we call roll, no rotation about Y, we call that pitch. So we have 3 degrees of freedom out of 6. We have X direction motion, Y direction, which is lateral motion, and then yaw rate or yaw motion, rotation about Z. So 3 degrees of freedom. Besides that, we make another simplification. We make it bicycle. When we have no roll, we don't need 4 wheels on the side. We can make it bicycle, 99% exact. So whatever we do is bicycle model. I show you the equations, but before going further, I have to mention a few things. First, A1, A2 shows the position of mass center, critical information. A1 and A2, or position of mass center, makes your car understeer or oversteer. It is stable or unstable. Our cars, all of them are understeer, stable. So that's one. The other thing is delta. Delta is a steer angle. It is in your hand. We dictate what is the delta for this system. So delta is input from the driver. We dictate delta. And then V. V is the velocity of the car at mass center. V has 2 components, Vx. In my control, so you control Vx. And Vy, which is lateral velocity associated to beta. Beta generates the angle of velocity. So V has a Vx input in my hand, Vy output of this system. Comes from a steering angle. So beta is another output. Also yaw rate. R is the yaw rate. So angular velocity is the dimension. That's all. This is the equation of motion. Degree of freedom. Usually we must have Fx, which is traction force, and calculate velocity, but practically we determine Vx and we calculate the required force. Forget about that equation. These 2 equations clearly give you the information what we need. Lateral velocity and yaw rate. These are 2 degrees of freedom, which are output of the system. The first equation is independent of the other one. These parameters or coefficients are here. Look at these coefficients, which are going here. Take a look, A1, A2, C alpha front, C alpha rear, and the rest of them are the same. It means when you have a car, you have the mass center position, so A1, A2 fixed. C alpha F is side slip coefficient of front tire, so it is a property of the tire and pavement interaction. This is for front, this is for the rear, because it's a function of normal weight, so usually these 2 are different, even though you are using the same type of tire. Okay? So when the car is given, the pavement is given, these coefficients are given. There is one parameter Vx, which must be given by the driver. So you put them here, differential equations are set. Steady state condition means nothing is changing with time. So everything, every derivative, everything with a prime, with a dot, would be 0. Put these three 0, simplify these equations, these are steady state. So my job today, or objective, is to show if the solution from here can be trusted enough to be substituted for the solution here. What is the purpose of that? I will tell you later. So this is objective. How close are the vehicle's steady state behavior with this to the transient behavior with this? And what is my assumption? Assumption is that vehicles are always at a steady state condition or so close to a steady state condition. This is true. When we drive, our car is always close to a steady state condition. We don't have that many transitions. The purpose of that is to use it in auto-driver algorithm. This is another assumption. Assumption is that cars or vehicles are always turning about the center of curvature of a road. So when you have a road, it's a mathematical line. At any point, there's a curvature center. If you are going to follow the road, you must turn about that point at that time. So this is the assumption. How we can design a system to do this job for the driver. So driver are not steering the car. Steering would be done by a computer. It's so easy. The idea is so easy. It's a line. At any point, the curvature center is given. We have to adjust. The computer has to adjust the steering angle to find the center of rotation of the car, put it at the center of rotation of the road. It looks simple. What is the center of rotation of a car? Kinematically, if you have a front wheel steering car, then perpendicular to the front wheels must intersect on a line on the rear axle. This is the center of rotation of this car kinematically. As you can see, by changing the steer angle, we can move this point forward or backward 1 degree of freedom. 1 degree of freedom we have. We can control the center of rotation of this car by changing the angle. The condition between these two, very simple geometric, it's called Ackermann condition. A stolen idea by Ackermann. Different story, I put it on my book, you can read that. If you have four-wheel steering, that condition is a little bit complicated, but still simple enough to implement. Center of rotation. What is the advantage here? The advantage is that when you have steering in front and rear, you have 2 degrees of freedom. You can adjust these two to put the center of rotation wherever you want in the whole plane. You are not committed just to one line. You are not restricted to one line. So theoretically, four-wheel steering is much, much easier to handle auto-driver algorithm. This is what I did in 2010. Then, Hormoz, who is working with me, and most of this work today I'm presenting was done by Hormoz. Hormoz was going to put this auto-driver algorithm for front wheel steering. Look what is the problem. If you have, this is the car. If you have this point for center of rotation of the road, and this point is not on your rear axle, it's impossible to turn about that. You have to move your car to bring the center of rotation of the car to that curvature center of rotation. But here, in four-wheel steering, no matter where you are, what is your angle, orientation, position, always you can adjust this to turn about curvature center of the road. So you see simplicity here and difficulty there. But our cars are not four-wheel steering, so we must do something for front-wheel steering. Let me give you an example. If you're turning on this elliptic shape, what you do is to adjust the steering wheels to turn about curvature center of this at that point. This diamond here shows the curvature center of this road. So practically, you're looking at the road, it's elliptic shape, but actually you are turning about this point. When you move, this point moves here. So you are moving in this direction, that curvature center is moving like that. It's what's happening. So it is very simple. If I have this road, I calculate this, And wherever I am, I adjust front and rear steering angles somehow that kinematic center sits at the right point. So your car can follow the path. An example, this is that ellipse, and assume that we are moving with a constant angular velocity there. Some calculus gives you position of the curvature center. Some transformation will give me position center in body coordinate. I forgot to mention that whenever you have a car, there is a body coordinate attached to the car. We calculate everything in that body coordinate. It moves with us, but sometimes we have to go to global coordinates, so there is a transformation. It's a little bit confusing, but in two-dimensional, it's not that hard. So these are curvature center globally, comes from the road. These are curvature center locally, goes to the body coordinate. Now I can adjust the steering angles, and these are the steering angles for four-wheel steering. This is what I've done before. So you can follow this path. It's not happening. Why it's not happening? But because there is something in car, and that's side sleeve of the car. No car is going perfectly as we decided or we planned. What happens is that we have 3 points. One is the curvature center of the road. Let's assume that your car starts from here and it is supposed to follow this circular path. Very simple. Center of curvature is 1 point. It's not moving. So we assume that we must have a constant front and rear steering angle forever, and we are supposed to follow this. When we set these angles, at very, very low velocity, we are going to follow this. But when you push the pedal, if your car is understeer, you move away from the road. And you are actually turning about another point, which is dynamic center. But practically, we adjusted kinematically to be here. As you can see, this is the point you are supposed to turn about. This is the point you are actually turning about. And this is the point that kinematically you are supposed to turn. What happens is that kinematic center of rotation will turn about actual center of rotation. Our goal is not to put this on that. Our goal is to put this on that. So to do that, we must do dynamic analysis. Here is the problem. Dynamic equations are so hard to solve for every cases. We need some approximation. My question is this. Is steady-state equations are good enough to do the calculation, put this here. To go inverse dynamic, we need simplifying equations. Anyway, these are the equations for front and rear steering, some transformation, as you have seen, and another integration to find the position of the car on the road. And what happens is this. You see the bicycle model here. It's supposed to be circle. If you don't see this circle, it's because of the resolution. It's almost circle. These two lines are just perpendicular to the front and rear axle. And in this case, it's front and rear both steerable. So we set everything, and what you see is following the path correctly. Why? Because my speed is very low, close to zero. So kinematic calculation works very well. But when the speed is higher, this is what happens. Speed in this case is 20 meters per second. This is what happens practically. Now our job is to bring the dynamic center to the road center. How we can do that? What is in our hands? The only thing we have is a steering angle. We have to steer more, right? We have to steer more to bring the dynamic center to the road center. How we can calculate that? We have to go inverse dynamics, back and forth, trial and error, and find out how much steer angle we need to implement to bring these two. We did that, and this is the result. Same car, different speed, different steering angle, and both of them are following the path according to our wish. How you can adjust the steering angles in front and rear for both of these cars at different speed is calculation based on inverse dynamics. So you got the idea that the steer angle is a function of velocity. You must have a calculation, velocity, and then proper steer angle. Okay. That's the same, just as a show off, you can see the same problem. So this problem was done and solved beautifully, but the path was so simple, so calculation could be done analytically. Now, if you have a front wheel steering car, I told you that kinematically, this is my car, kinematically, the steering center of the car is on rear axle here. Not this, yes, lower. But practically, when you push the pedal, when you go faster, the center of rotation of the car is moving on this line. It's not a line, it's a curve, but close to a line. When you are driving with 40 meters per second, 150, 60 something kilometers per hour, you are actually turning, when you are turning your steering wheel 5 degrees, you are turning about a point 90 meters away, around 15 meters in front of you. Clear? If you want to turn about this point, which is curvature center of the road, you have to adjust your speed to this speed, right? Or increase the steering angle. But point 1 is the maximum allowable, which keeps us linear. After 5 degrees, that speed, you are going to slide away. So there is a safety issue. You got the idea that there must be a proper speed for any point at a specific steer angle to put the dynamic center of rotation of your car on curvature center of the road. That was the definition of the problem. So you got the problem. Get back to the objective that we have. I'm going to show the result of the steady state and compare it to this to be used in auto driver algorithm for front wheel steering. I pick a car with these numbers close to a real one. A little bit exaggeration here, 1 meter, 1.5 meter. Usually they are closer to each other. But it gives you a very heavy understeer car, which is stable. So it's following my rule much better. According to the steady state condition, radius of rotation would be this, beta, which is lateral velocity, is here. Doing some calculation, you can find the curvature center or rotation center of the car. Please. And these are the results for yaw rate, rotation, radius, and beta. Wow, there is a maximum here, and there is a crossing zero. We as a, scientist, whenever we see a maximum, minimum, we are excited. Whenever a line crosses zero, we are excited. There is something optimal there. I'm not going to talk about that today, but it is just crossing the zero for here, and we call that critical speed. At that speed, your car is tangent to the road. Below that, you are inward. Higher than that, you're outward. Exactly at that critical, you're tangent. That's the best speed for that road. It's not our intention today. So you got the idea that rotation center of your car, how it's moving away from you. Let's try 2 maneuvers. The first one is a constant steering or a step input in the steering angle. Step input means from zero you jump to a steady state or constant value. There's a transition that you go finally follow a circular path because the steering angle is constant. Finally, you are going to have a circle, right? But practically, no human can do a jump in the steering angle. This is what we do. Very slowly, not very slowly, but in 1 second here, 1 second, we go from here 0 to 0.1 radian, and then we keep it constant. This is the function, mathematical definition of this steering input. H is heavy side function. Funny name. We were lucky, it's just a show off. We were lucky for that special case, we could solve it analytically. We don't need that, but we could solve it analytically. These are transition. These are
So how close are these two so simple now?
We can draw the curve and see what happens. This is yaw velocity. R sub s is a steady state yaw rate. And the red one is transition. Right? This is exact according to our model. This is a steady state. And this is the error. Of course, error goes to 0. Both of them eventually will turn on the same circle in local coordinate. And what is here? This is lateral velocity. The difference goes to 0, and as you can see, there is a difference in transition time, almost 1 second. You remember, in 1 second, you are going to change the steering wheel. So after 1 second, half a second it takes, or another 1 second it takes that input-output, no, the solution of two different models approach each other and are equal. This is radius of rotation, error 0, so they are going to turn about the same circle with the same radius. What is this? It's psi. Psi is angular position of your car. There is a steady state error there, or there is a lag. Which one is faster? Which one is faster? As I said, this is transient, this is a steady state. Wherever in these figures that you see, the transient response has a lag. It's lazy. It's behind steady state. Steady state is ahead of it. Psi is another integration of yaw rates, and then some transformation, some integration. You find the position of the car in the global coordinate, and this is in global coordinate difference between x and y. X and x steady, y and y steady, and we put them together to see what is the difference on the road. This is geometric difference. It's supposed to be circle again. The geometric difference, it's turning about around 90 from 0. I mean, 48 meters is the radius of that, and you see a little bit exaggeration here, but you got the idea. This part, transition, is shown here. So both cars are starting here, and one is following red one, which is exact. The other one follows the black one, which is transit. Not in scale, here I show the difference better. The difference is not just geometric. Time-wise, there is a difference. One of them has a lag, shows that in time also it's behind the other one. So steady state is in front of transient. And you see the time here. The radius of both circles are the same. The center are misplaced. Very good. After one round, they are catching each other. So that was the first experiment, doing some mathematical analysis, comparison these two and see how close they are. We found out that in time there is a lag, in geometry there is a displacement. Everything is related to the velocity and steer angle, which are input. If we make it slower, they are going to be closer to each other. If we decrease the speed, they are going to be closer to each other. For another example, I give you this input. It looks complicated, but it is lane change maneuver. Lane change maneuver. This is how we change the steering angle to do a lane change. And this is what you see for actual steer angle. And this is the difference after doing all of those calculations. Still, there is a lag here. I'm done. On time. Conclusion. Transient response is behind the steady state response, and it's a function of velocity and steer angle. We have to figure it out what is the condition for that to be to make sure that transient response is acceptable enough. And then the maximum difference of the responses in all cases was less than 8%, still for those numbers that we used. If for example, we are looking for a specific percentage, for example, 2%, we have to figure it out what is the boundary of a steer angle and also the velocity. The difference decreases by decreasing the rate of a steer change. Of course, you can guess it. What is the next step? First of all, we have to conclude variable steer dynamics. These two examples were for constant velocity, constant forward velocity. I told you that forward velocity is another input. So we have to do some analysis for acceleration maneuver at a constant steer angle. And then combine both steer angle variable, velocity variable, and analyze if there is a reasonable comparison between steady state and transition. Compare transient and steady state behavior for variable speed, as I said. Hormuz is doing that at the moment. Combine variable steering and variable speeds, of course. Determine the conditions in which the steady state equation provides reasonable approximation for transient behavior. This is my goal. This is our goal, to find the condition. Within that condition, we can accept this closeness. Then apply the steady state dynamics in auto driver algorithm. After this point, everything goes to auto driver algorithm. Apply this algorithm in lab condition, controllable RC vehicle. Apply auto driver in a real size vehicle, and then equip a real size vehicle with other safety issues. I'm done. Thank you.
Thank you, Reza, for a very impressive presentation. Any questions from the floor?
There is actually four different questions, but they're linked together. This sideward slip of the car is due to the centrifugal force. Second question would be, would it be advantageous to reduce the sideward slip? Number three would be, can you measure the sideward slip? And is there a difference between different, let's say, tire brands and cars?
I'm confused now, like you, but I repeat the question. The first one was, side slip is related to centripetal acceleration? Yes, that's right. Lateral, the main reason that we go out of the road laterally is that we don't have any mechanism to provide enough lateral force that we need to keep us on a circle. As I said, at any time we are turning about a point. Yes, side slip force is required to provide centripetal acceleration. Losing or saturating the friction capacity between tire and road is the main reason that we go outside. That was the first one. What was the second one?
Second one was...
I'm happy.
Was that your job?
Would it be advantageous to reduce the amount of side flexibility? If it could be done.
Yeah, this analysis was not in that direction. In our model, everything was linear. As long as you are linear, you can provide as much as you want lateral force. So this car is never going out of the road. We have to implement C alpha nonlinear to be saturated to show us that it's going out of the way. We didn't do that analysis, but of course, if we include that, it's different category. We don't need to work on steady state or auto driver algorithms. We have to focus on nonlinearity and saturation of the side slip capacity.
And would it make sense to measure the side slip?
Yeah, there are many research on that. Every single company is providing some control or measurement or sensor to calculate that, to prevent that actually. This is what we need. We want to prevent side slip and going out of the road. But yeah, it's not the focus of this research. But yeah, you're right, absolutely.
Simon?
Yeah, I had a bit of a follow-up question on that. In many vehicles now, and for the last 10 years, there's been automatic stability control, where companies like Robert Bosch have, through a lot of development work, effectively taken the steering input out of the human once the thing starts to go out of control. So do you know, in companies like Robert Bosch, are they using a non-linear dynamic analysis, or is it all coming back to empirical models, measuring the side slip, measuring the yaw angle, doing calibration of their lookup tables to get the automatic stability control?
the question was this. There are some companies who already implemented some mechanism to prevent going out of the road. Are they using nonlinearity in their equation or vice versa? What are they doing? They're basically trusting vision. That's what they do. In this model, this car is blind. We are just giving everything to it mathematically. But if we equip the system with some vision, then we can adjust or put the feedback to control and bring it back. Where is Milan? Milan is doing that in the lab to follow the mobile robot, the line, and it's using a lot of sensors to do that. Here we don't use the sensor.
But that's more for autonomous vehicles, not in a scientific condition. But many of the cars out in the car park there have got automatic stability systems which take over and they'll automatically brake 1, 2 or 3 wheels, possibly put a steering input that isn't coming from the vision. It's coming from somehow knowing that the vehicle is not doing what the driver wants it to do.
True.
So it must be.
Yeah, interaction between tire and road. That's right.
So
That's
they're
right.
doing that just with a lot of sensory inputs and then lookup tables and calibration to try to tweak those. We've all seen the kind of lane change manoeuvres Mercedes-Benz adverts where, you know, with ABS, without ABS. But that doesn't have vision. So there must be.
Yeah, true. Vision was main part, but there are a lot of sensors we add to the system to follow what we want it to do. It wasn't the purpose of this. Here we wanted to take the role out of the driver. So driver can eat or drink, but watch the road, he's controlling brake and pedal, but the steering will be done automatically. Of course, if we equip the system with some other sensory systems, we can make it much better. Maybe John, I'm sorry, Tino, I forgot your fourth question.
No.
That's it. John, please.
Thanks, Reza, as usual, on beautiful maths in your presentation. You compare the steady state solution to the dynamic solution, both are theoretical. You probably partially answered this in your last slide, but I'm just wondering, have there been any measurements taken, experimental measurements, to compare the predictions of your models with what actually happened? Or is that coming later?
The question is this.
The experiment, everything was analysis, mathematics, modeling, and so on. No, we didn't do any experiment.
We didn't do any experiments yet. It's on the way. Yeah, when we finish that, the theory still needs another couple of years to be solid. Yeah, to be able to implement that. But next step would be doing this in experimental lab environment on RC, radio control cars, because we have control on the pavement in the lab. When we go to the road, actually, we can approximate the pavement condition. But this is the next step.
Sorry, just the follow-up. The practical application. I mean, are you looking towards the sort of device that Simon was saying, like some sort of automatic steering system that means we avoid accidents? What's the practical application you have in mind? Or
what is the practical application of this is taking this action out of the driver's function. Today, let me explain. The explanation is this: the second thing that makes drivers fatigue or be exhausted is a steering, rather than vibration, which is the main reason. The second one is the steering. So many years ago, probably 20, 25 years ago, having ABS, some system that controls brake, was strange to us, but it's working very well. To have a system to control your speed, means cruise control, was strange 50 years ago, but it's working fantastically. To have a system to take the road when you are driving not in the city, between cities, on the road. So road is actually a line mathematically given to us, and you don't need to drive to road. It's following the path automatically by itself. So this is the final step. If you can invent or put such a system of control to follow the path without the driver steering wheel. This is the goal.
Sorry, Reza. Can I add up something to the answer?
Please.
Yeah.
What was the main driver of everything?
Now, I've always been scared of these questions during the whole time I was doing my PhD. Reza knows that as well. So I've thought about these. One of the main things that this can be used is in places like, say, deserts when there's no roads. So you can actually come up with a mathematical equation for the road that you want the car to actually go through to get to the destination, like the DARPA challenge, and then have some vision or sensors to avoid obstacles. So that's something else that this can be used for, I guess.
Okay, very good. Do you want me to give you the last joke? Yes. Oh, sorry, Ali. Please,
now
go
I'm
ahead.
standing between your joke and everybody
No,
else.
no, no,
This is
no,
not
no,
an
no,
outdoor
no, no,
position.
go ahead.
Now, I was about to say that, if I understood your presentation correctly, and the whole premise of this research was that you want to use a steady state solution in place of the transient solution.
That's right.
And see, is this good enough?
Yep.
Right? Then how are you going to become the good enough?
We need to.
This goodness, how are you going to characterize this goodness of it?
Yeah.
And I was thinking that unless you bring the control into this, it'd be very hard to say what response would be good, wouldn't it?
Myself? Yeah, okay. Okay, the question was this: how are you gonna find out if they are close enough? That's what I said. One of the outcomes would be define the condition of limits for steering wheel change and speed change, that the difference between these two solutions are within a specific limit of acceptance, 1%, 2%, or so on. For cars, having the car here or 5 millimeters away wouldn't make any difference, but 5 meters away makes a difference. So first of all, we have to show that mathematically we are close enough within centimeter. What is the condition to have that? And then we have to do it experimentally to make sure that it actually happens. Of course, in experiment, we have another sensory system to make sure that if it is too away, we bring it back. So feedback. Here, you didn't see any feedback. The control system that you can think of was blind. It was one line. There were no feedback. Adding feedback, I'm sure that in experiment, in real situation, you can make the system much better. But before any feedback system, I have to make sure that mathematically, modeling...
Close enough to go for next step. If you are away, forget it. But if you are close, so far we are considering that these are close enough to go for next step. I'm not sure if I can finish. If I take 2 more questions before we finish. No question. I answer for household solutions.
One basic line comes to make this all not the way where when you go to start and we are in the various can this model direction be applied to it, or do you have to start copying a ground up?
Yes, very good question. The model that you used here was very simplified. The question is that in real situations, the cars are not similar to your planar model. But I mentioned that 99% this model is close to real situations. So if you do experiment on the real car and do analysis here, the result is so close. The other step after this is adding rolls to your car and see what is the action of the rolls to this. But the model is exact enough, and probably it is 70 years that we are using this model and analyze everything. But yes, real situation is always totally different. In every university, I'm sorry, in every university, we as a supervisor, we sit here, students are coming into the picture, we get their PhD, or we don't like them, we reject them. So they are coming and going, we are here. But in our school, there is a genius person who is not here, what I'm talking about, who is here and supervisors are coming and going and coming and going. That guy was working for a while with Lucian, and then he sent him to search. And then he started to pick another supervisor. He accepted another supervisor, Kevin. And he sent Kevin to the United States. And now he's working with Tesla. And I'm trying to put Alberto as a second supervisor. So I'm sure that next day we are going to have a line. Professor wants to be the second supervisor or next supervisor. No question.
Okay, well, my question. Yes, about the application, of your theory, and I was wondering how valid it could be the results.
The results of some experiment on a small, say, model, something that maybe fourth-year student can do as a fourth-year project, for example.
That was the question.
Yes, that's the question, basically.
That's exactly what we're going to do. When we are sure, probably by end of the year or mid of the next year, when we are done with theory, then we go and make an experiment in the lab with small cars,
okay.
yes, and computer control and so on. At that point, Milan Simic is going to take the role. When it is done there, and we are happy with that, then we go and implement in real side.
Okay. And the second question I have is that, now you mentioned four-wheel steering. Now, does it have attractions, and why it's not being done?
The question that you said that four-wheel steering is simpler to control, to maneuver. Yes, it is. Around 1980, it came to the picture, and so many companies started to working on that. Mazda was working on that for a long time. Mercedes did that, but it went out of the picture because of price. And at that time, theory was not completely developed for four-wheel steering. Look what happens. Here, front wheel is my hand, but rear wheel can have any angle at the moment to make the center of rotation wherever we want. At that time, 20 years ago, 30 years ago, what they did was make these connected, so the rear was proportional to the front. So you change the front, rear was proportional to that. It wasn't a control two-dimensional, it was still one-dimensional control. But they had a switch to do the rear according to your speed. So at low speed, this was opposite. At high speed, they were parallel, but different proportion. So they implemented something, but they didn't make it fully functional, fully two-dimensional freedom. So they forget it because of, repair was a disaster, computer needed, so many problems.
Well, I'm sure after this seminar we all will be different drivers, so please don't think of the differential equations and just concentrate on your driving. Milan, you want to say something? Your name has been mentioned several times.
The last one, because I mentioned a couple of times, thanks to Reza, we actually started working on this project from the very same day when Reza came to the idea. He put me in, and I'm very thankful for that. The idea is, there are a couple of questions, so why do we need that? Basically, with this algorithm, we have better starting point to apply feedback from other sensors. So instead of, when we don't use algorithm, we know this is the curve that we follow. But that's not the curve that we go. Actually, vehicle go the other one, as Reza shown. So knowing that in mind, then we apply the feedback from the sensors. And yes, ordinary cars have a lot of sensors. They have gyroscope, they have speed sensor, and they have feedback. But do they use this algorithm to correct the target curvature? That's the point, the target line that it should be followed. They probably don't use that, otherwise we would know about it, because we have experts here, and that's the starting point, instead of the wrong assumption that vehicle will go that way. We know that it will not go that way, and that's our starting point to apply feedback now.
Well, thanks for the tip, Thanks for that explanation. Okay, well, let's thank Reza.
Thank you.